This week, those kids are going to show me where natural gas comes from. Natural food, I suppose. Then we'll see why alternating current can't make up its mind. First, though, a peek at traffic signals. I used to be quite a traffic stopper myself.
Driving home one night, I had one of those sudden realizations. I'd never seen a burned out traffic light. It made me realize that somebody must go around changing the bulbs before they burn out. That was only the first interesting thing I learned about traffic signals. You know, if you've driven around a city for a few years, you've seen thousands of traffic lights and obeyed them without even noticing them. The first interesting thing, they're this big. Not only that, these are the small ones. There's usually one with a large red light at each position on the intersection. The bulbs are 67-watt jobs, specially designed for traffic signals. The large red one uses a 150-watt bulb. And the assembly is aimed at a spot on the road where it's most important for you to see the signal. The units are modular, and that allows for building signals with extra lights for left turns and other special symbols. Now, even though modern microelectronics has invaded the world of traffic signal control, there are still some of these controllers sitting around on street corners. These controllers are mechanical, and even though the new style controllers are a lot snazzier and have a lot more tricks up their sleeves, these are more interesting to look at because they have moving parts. This switch is the heart of the mechanical controller. It uses a group of wheels in contact with a bank of switches that correspond to the lights. Wherever a section of wheel's been broken away, the contacts will close and the corresponding light will come on. Okay, let's pretend. Let's pretend that the lights are at the intersection of Main and Cross Streets, any town. These are the 6 switches for Main Street red, yellow, and green, and Cross Street red, yellow, and green. Now there are 12 positions on the wheels to allow for extras like flashing green and pedestrian signals. This is a simple intersection that only needs 6 positions, but we still have to use all 12 positions. So some of the positions will do nothing. We start with Main Street green and Cross Street red. Now Main goes red, with Cross Street still red. Okay, everybody stop. Cross goes green. And then it goes yellow. Oops, there's a couple of those do-nothing cycles. There, Cross is yellow. And then finally Cross goes red, and the sequence repeats. Now, there are 12 segments on the cam wheels that can be broken off, and there are several ways to do that. You might think maybe we should break off segments so the yellows are on for a shorter time than the reds and the greens. But the cams and the switches only control the sequence, not the times. The cams are rotated by this solenoid. It pulls against a ratchet whenever it gets power. There are 12 teeth on the ratchet corresponding to the 12 positions on the wheels. Okay, the solenoid is operated from a motorized timer it's surprisingly flexible for a mechanical device. The time it takes for this drum to go once around is set by a gear at the back. This gear is set for 60 seconds. The drum has 100 slots in it, and these keys can be inserted at any point. As the keys pass a switch at the top, they trip the solenoid. Now, since there are 12 positions on the cam switch, there have to be 12 keys on the drum. Some of them just use up those extra positions. The ratchet advances, but no lights change. Next time you're leaning on a controller waiting to cross the street, you'll hear the ratchet advancing. Notice that some of the clunks don't affect the lights. If the sequence that's picked results in traffic jams, the gear at the back of the timer can be changed, or the keys in the dial can be set to different positions. This particular controller can accommodate 3 different timers and a clock to choose among them at different times of the day. We'll say rush hour, normal, and overnight. Now, since the lights are on for different percentages of the time, the timing drum and the broken out cams on the shaft have to be in step. Otherwise, the controller might be holding Main Street yellow for 60% of the time, with everything else correspondingly mucked up. If that happens, the unit will stop on Main Street green and wait for this special key up here to come around. It's special because it's longer and it hits a different switch. The mechanical controller can be outfitted with a lot of different options too. Multiple timers, vehicle sensors, and pedestrian buttons so the lights only cycle on request. And the controllers can be hooked to each other as well to change the lights at different intersections in sequence. Oh, this little motor and cam, the advanced green flasher. The 4 painted switches at the end of the camshaft are set up to indicate which of the 12 positions the camshaft is in. Who needs to know that? Well, the central computer, of course. Twice a day in Toronto at rush hours, the computer takes over all of the traffic signals. Communication is done over a pair of dedicated phone lines to each intersection. They have a big phone bill. The 4 switches on the cam signal what state the lights are in. And then the computer disconnects the local timer and pulls the solenoid that advances the ratchet itself. It's rush hour in the computer room, and the computer is busy capturing intersections without disturbing the local sequence. It wouldn't help the flow of traffic to have a brief 2-second green, for instance. The computer adaptation of the mechanical controllers is pretty ingenious. The new solid-state controllers are computers themselves. The operation of the computer normally isn't noticeable till it fails. Then we get a good demonstration of what 1,500 unsynchronized intersections can do to a city. Since the new computer took over in 1980 or so, there haven't been any huge failures. The new controllers are pretty spiffy. Listen to some of this. Time of day, day of week, week of year. Battery backed up RAM. 0 to 127 in 1-second increments. Preemption, 4 independent plans located on programmable PROM. Setability, year, month, day, hour, minute, and second with daylight savings time conversion automatically implemented. 10-week programs and 35 exception days. Once again, microelectronics takes over. Fantastic. But boring. No moving parts.
Consumer Detroit.
This boiling water is in Toronto. 6 days ago, the gas burning under it was in Alberta. How does natural gas get from Alberta to Toronto? Well, there's a pipe. A $2.6 billion pipe. Natural gas is collected from various wells in Alberta and begins its journey to the east. All along the way, there are taps on the line where gas is fed to local gas companies who then pipe it to industry and homes. Out west, there are as many as 5 parallel pipes carrying gas. As more gas is tapped off along the way, the number of pipes decreases. We got a once-in-a-lifetime chance to follow the gas across the country. No, we didn't take a trip. Instead, we borrowed a lot of archival footage from Trans-Canada pipelines. Natural gas comes from here. Well, I expected something a little more dramatic too, but this unassuming pipe is a natural gas wellhead. From the wellhead, raw gas is piped to a nearby, more dramatic place, the processing plant. Natural gas contains methane, ethane, propane, and butane, which can be processed into almost 100 different useful products, from antifreeze to movie film. At the processing plant, ethane, propane, and butane are removed, leaving the methane to be piped east. Large quantities of sulfur are also removed. From the western processing plants all the way to the east, most of the pipeline is buried, no matter what the terrain. The gas that runs our eastern industry and heats our homes travels 4,500 kilometers, quietly under roads, rivers, and fields. distance covered by the pipeline system is 4,500 kilometers. But because of the parallel runs, the length of pipe in the system is well over 10,000 kilometers. The pipe diameter is about 1 meter. Depending on the terrain, different installations are used. In rocky areas, the pipe sits on polyurethane pillows. In wetlands and swamps, concrete weights hold the pipe in place. Underwater, concrete collars are used to sink the pipe. After the pipe is buried, there's little evidence of the artery that carries 25% of Canada's total energy. The only clues along the way are tap-offs to local gas companies and 49 compressor stations. The compressors pump the gas along the line. Some of the compressors are run by modified jet aircraft engines. They don't normally fly through the air like this. This one's being installed. After installation, they're difficult to see because they're shrouded in a noise-blocking enclosure. The most awesome machines are the oldest compressors, the reciprocators. These are similar to a car engine, a 3,000 horsepower car engine that's the size of a house, but nevertheless similar. This building houses 3 of these units. With the exception of a few electric compressors on the system, most of the units run on natural gas. This small gauge is indicating an output pressure of 6,000 kilopascals. That's almost 1,000 pounds per square inch.
Gas control. Yeah, 116. You lost your B there, eh? How long will it be? 8 to 10 hours? Okay, thanks very much. We'll get station 112 online right away.
The individual compressor control rooms across the country report by telemetry and telephone to the Gas Control Center in Toronto. The controllers here coordinate gas demand, maintenance schedules on the pipeline, and other factors affecting the operation to keep the proper amount of gas flowing across the country. All of this fits the Acme principle of discovery. The last time you cleaned behind the gas stove or hung a shirt on the gas pipe in the laundry room, little did you realize that those pipes stretched all the way to Alberta and are actually among the longest pipes in the world. Quick survey around the office revealed the fact that everybody knows that the power in their homes is 60-cycle alternating current. Half of the people surveyed knew what that was, and only one person knew why it was there. 15 years ago, I could have told you how alternating current kept our clocks and turntables running on speed, and that many of the motors around the house would only work on AC. But times have changed. Most modern electric appliances either require DC, direct current, or they don't care whether they operate on AC or DC. There's one good reason left why the electric company delivers alternating current to our homes, but it requires a bit of a demonstration. That's the effect of too much current flowing in a wire. One solution to the problem is increase the size of the wire, but there's another solution. The work that's done by electricity is measured in watts. And wattage is determined by multiplying current by voltage. Scientifically speaking, volts times amps equals watts. Now, practically speaking, as far as you and I are concerned, we only care about wattage. Wattage does the work, and we're charged for electricity by the watt hour. The heating effect that burned my little wires over here was caused by the current that was flowing, the amperage. So, I can transmit the same amount of work over a smaller wire by sending relatively high voltage, low amperage electricity. Unfortunately, we can't use this high voltage power in our houses because there's a little quirk of high voltage electricity. It likes to jump right through the air. So we want lower voltage electricity around the house, and the electric company wants high voltage on their towers and poles. The solution to all of this problem is George Westinghouse's invention, the transformer. And the transformer is the key to the great alternating current mystery. When a current flows through a wire, magnetic field results. The reverse is also true. But notice, magnetic field can only cause a current while it's moving. That's one of the laws of the universe, and I can't do anything about it. If I put these two bolts end to end, I get an interesting method of transferring power. The battery is going to cause a magnetic field to move outwards in bolt number 1, and it's going to cut across bolt number 2 and generate a current. Briefly, as soon as the invisible magnetic field grows to its maximum size, it's no longer moving, and the current ceases. When I make the field in bolt number 1 collapse, another blip of current flows. The electromagnetic effects are proportional to the number of turns of wire on the bolts. Here's what's inside a transformer. 2 coils of wire on a common iron core. Now, if the 2 coils of wire have the same number of turns, all we have is an interesting scientific effect. If the 2 coils of wire have a different number of turns, we start to get somewhere. The voltage out will be proportional to the ratio of the turns of wire. In other words, if I put 1 volt into these 10 turns of wire, I get 10 volts over here from the 100 turns of wire. Now, by the law of physics that states there's no free lunch, I gain 10 times the voltage at 1/10 the current. But by the volts times amps equals watts formula, the wattage remains the same at both ends.
Hogwash!
Well, the wattage remains almost the same. Some of the electricity goes into heating up the transformer. As a matter of fact, this little model would be so inefficient it would probably melt instantly. A real transformer will have thousands of turns of wire. This was a real transformer. It has a 150 to 1 turns ratio approximately. About 100 volts in gives 15,000 out. Transformers are the reason that all of the electricity in our homes alternates 60 times a second. This is a little more natural than it sounds, actually, because all of our electricity comes from rotary steam or water-driven generators. And as the rotor turns with the magnets on it, the most natural thing in the world to generate is alternating current. Now, my oscilloscope shows a pretty choppy version of AC. Real generators have more than 2 wire-wrapped bolts and more than 4 flaky little magnets. Here's some real AC. This is what comes out of the plug in the wall. Why 60 cycles a second? I don't know. The frequency has to be high enough so that the lights won't flicker visibly, and low enough to not be too annoying as electrical things hum away. But if anybody knows where the number 60 came from, they're just not talking. The voltage at the wall plug is supposed to be a nominal 120 volts, but a careful measurement on the oscilloscope screen shows that the voltage actually peaks up at around 170 volts. Because alternating current is constantly reversing directions, it spends some of its time not doing much work. The effect of AC in a heating element or incandescent light bulb is only 0.707 of its real peak value. So, just to be nice, they're giving us 170 volts, but they're calling it 120 volts, just to be fair. Incidentally, I know where the figure 0.707 comes from, only I'm not talking. Heating elements heat because of the current flowing in them. They don't care which way the current's flowing, so they can use alternating current directly. An incandescent bulb can just be considered to be a special case of a heating element. The filament, heats up to the point where it gives off light. Here's an interesting trick with AC, though. a 10-cent component called a diode will let current flow only in one direction. And by inserting a diode in the circuit, the wrong way half cycles are blocked and the bulb runs at half brightness. Simple dimmers that have a full and half position use the 10-cent diode. They don't charge you 10 cents for it either. Huh. Now, a lot of things require a steady source of current, direct current, the kind that comes from batteries. Putting the diode in the circuit gets us halfway there. Current's no longer going backwards and forwards, but it's still going on and off. A tape player running on this kind of power sounds like this. To finish conditioning the current requires a capacitor, or condenser if you're over 50 years old. The capacitor is a little like a rechargeable battery with a very short life. When the AC cycle's at its peak, it charges up, and then it powers the device while the AC is busy dipping to nothing. Now, if the capacity is too low, the effect isn't perfect, and you'll still hear some humming. Now that I've just told you what's wrong with your tape player, there's one more thing to know about it. My little demonstration with one diode actually throws away half the cycles. There is an arrangement of 4 diodes that's used in most power supplies that folds those unused half cycles in the correct direction. When a power supply like that starts to hum, the hum is double at 120 cycles per second, because that's twice 60 cycles. But I still don't know where the 60 comes from.